Now we're getting into a discussion of fluids. And you know probably that materials have three phases. And these are solid, liquid, and gas. And if the pressure doesn't change, you can go through these different phases of materials by, you can go from 1 towards 3 by increasing the temperature. So at a constant pressure, you know that, let's think of water. At regular atmospheric pressure, it's a solid. Ice, until the temperature gets up to 0 degrees Celsius or 32 degrees Fahrenheit. Then if the temperature keeps going up past that point, it's a liquid. It's liquid water. And then once you get up to another point at atmospheric pressure, that is at 100 degrees Celsius or 212 degrees Fahrenheit, that liquid boils and that liquid water becomes a gas, steam. We here are concerned with liquids and gases. So what is it about liquids and gases that's different than solids? Liquids and gases allow molecules to flow past each other. Flow past each other. And so we're going to give those the name fluids. They flow. And the first property that we're going to talk about with fluids, so the first key property of fluids is the pressure. Okay, so what is pressure? So I think to imagine this, imagine blowing up a balloon. All fluids have pressure. And so as you blow up a balloon, you're increasing the air pressure on the inside of the balloon. Remember that the atmosphere also has a pressure that's pushing in on the balloon. And it's always, whenever you have an enclosed space with fluid inside and outside, there's sort of a push and pull going on. I mean, it's really both pushes, a push out from the inside pressure and a push in from the outside pressure. But you always have this battle between these two pressures to see whether this thing explodes or implodes or stays in equilibrium. In the case of a balloon, as you blow it up, you increase that inner pressure slightly higher than the atmospheric pressure, and that pressure pushing out from the inside stretches the walls of the balloon. We measure pressure so pressure is the force per area that it applies to the surface. So it's not just a measure of force, it's a measure of force on a specific area of the surface. The SI units of pressure are newtons per meter squared. And since, in certain areas pressure is used a lot, they give that its own name, pascals. So 1 Newton per meter squared is 1 Pascal. and it's represented as P lowercase a like that. Now, the pressure that's applied by the atmosphere to an object is surprisingly big, I think, when you hear about it for the first time. So atmospheric pressure is a lot. So atmospheric pressure is the standard atmospheric pressure, kind of the average atmospheric pressure at sea level, is 1.01 times 10 to the 5th pascals, which is 101,000 pascals, which means if you think of a surface that has an area of 1 meter by 1 meter, think of a square area of 1 meter of length on each of the sides of the square. Atmosphere is applying 101,000 newtons of force to that. So you might think, well, why doesn't that pin us down to the floor? Why are we able to move at all with that crushing force acting on us? And the key is that for any object, so let's think of something like this. Let's think of this 1 meter by 1 meter surface, like a piece of cardboard or something. Okay. The force acting on this from above is this really huge force of 101,000 newtons. Okay. But the reason you're still able to pick this up and move it and you don't notice this pressure is because acting on the other side of this cardboard is also 101,000 newtons. So the only time you notice this pressure is when there's a pressure difference between what's acting on one side and what's acting on the other side. Think back to the video I showed early on. One of the first videos I showed was the demonstration that all objects fall with the same acceleration if there's no air resistance. The way they showed that, so think back to the free fall video. They removed all the air from inside this huge building. And so let's think about what's happening on two sides of just one of the walls of that building. So let's imagine that this wall I certainly don't know what the dimensions of this building are, but let's say that it looked pretty tall. Let's say it was 10 meters tall. And let's say the wall going back had a length of 20 meters. Okay. In normal operation, the atmospheric pressure is present on the outside of the building, pushing in, and it's present on the inside of the building, pushing out. And so you can calculate the force that the pressure applies to this wall by just multiplying the atmospheric pressure times the area. Okay, so there's a force pushing in. So this is the outside of the wall. And over here is the inside of the wall. And now let's imagine what's happening once we've removed all of the air from the inside of this building. So if there's no air, there's no fluid in there, and so there's no pressure pushing out. So there's no force pushing out on this wall except the forces holding the walls together, you know, the nails and whatever is used to hold the building together. So let's calculate what the force is that atmospheric pressure is applying to this wall from the outside. If you take 101,000 or 1.01 times 10 to the fifth pascals and multiply it by an area of 10 times 20 meters, you get a total force pushing in of 20.2 million newtons. Okay, and now it makes sense if you think back. The narrator is describing how strong this building had to be, what materials they had to use to make this building able to withstand these gigantic pressures. Well, it doesn't have to withstand any kind of pressure when the pressure is the same on the inside and the outside of the building. But when you remove all the air from the inside, suddenly the only force from pressure is 20.2 million newtons acting in. And the construction of the building has to be able to withstand that force. And that's why the walls are very thick, concrete, reinforced by aluminum. Another way that you've seen this sort of competition between inner and outer pressure is cases where you kind of imagine yourself, like if you imagine a plastic soda bottle and you suck on that and it sucks all the air out of the bottle, and as you suck the air out of the bottle crinkles up. Well, there really is no such thing as you sucking the sides of the bottle in. What's really happening is you're taking the air out of the inside of the bottle, and since you're reducing the pressure on the inside of the bottle, the atmospheric pressure on the outside is now compressing the bottle. It feels like you're sucking in the sides, but what's really happening is just you're continuing to have a large pressure on the outside of the bottle while you reduce the pressure on the inside. Okay, well, the first fluid analysis that we're going to do involves fluid statics. So we're going to start out by fluid statics. And statics just means at rest. And so we're first going to do some calculations involving fluids that are not moving. We're not talking about fluid moving through a pipe yet or anything like that. We're just talking about, imagine like a liquid or a gas that's enclosed in a tank and it's staying put. Then what's called the hydrostatic pressure is the pressure in the fluid at rest. And so the first thing we're going to consider is imagine a column of this fluid. So here is the column, and this is entirely full of this fluid at rest. And we have 2 points in here. Let's say we have a point that's higher and a point that's lower, just compared to the direction of gravity. And the pressure at the top point I'm going to call pressure high. And the pressure at the lower point I'm going to call pressure low. Okay. And in a static fluid, the pressure of the lower point is always going to be greater than the pressure at the higher point. Imagine swimming to the bottom of the swimming pool, and you know from experience that the pressure is higher as you go down. That's the effect that I'm talking about. And the relationship, we can actually calculate the relationship between these two pressures. The relationship between the pressure at the lower point and the pressure at the higher point is that the pressure at the lower point is equal to the pressure at the higher point plus the density of the fluid times the acceleration of gravity times h, where h is the difference in heights of these 2 points. Okay, so this is the first key equation that we're going to use. This rho is the density of the fluid, and density is mass divided by volume, which means that in SI units, density will be given in kilograms per meters cubed. G is 9.8 meters per second squared, and H is that change in height. Okay, so let's see an example where we use this equation. So given that standard atmospheric pressure is 1.01 times 10 to the 5th pascals, how many times the atmospheric pressure, and I'll just call that PATM, is the pressure first 30 meters below the surface of the ocean, and second 150 meters below the surface of the ocean. So we're going to calculate how much pressure a diver is dealing with at these 2 different depths. By the way, 30 meters is a depth that people can scuba dive to. 150 meters is a depth where welders and professional divers need to descend to perform repairs on oil pipelines and things like that. 30 meters, people can scuba dive to. Knowledgeable scuba divers, that's not too big a deal. 150 meters, however, for the people who work on the bottom of the ocean, working on pipelines, they actually have to go through a long process of pressurizing their blood, and then they live at that pressure for up to a month without ever returning to atmospheric pressure during that time. And then when they're done with their month, they go through a long process of returning their body to atmospheric pressure. So these kind of represent sort of different levels of human diving ability. Okay, so for the first one, we know that the pressure at the depth, so 30 meters below the surface of the ocean, is equal to, I need to give density for seawater. Okay, so the density for pure water is 1.0 times 10 to the third kilograms per meter cubed. That's not what we're talking about though here. We're talking about seawater that has salt in it. So the density of seawater is a little bit higher because of the dissolved salt, and it's 1.03 times 10 to the third. Okay, so the pressure at 30 meters of depth is equal to the pressure right at the top of the water, which is just atmospheric pressure, plus the density of seawater times 9.8 meters per second squared times the distance in height, which is 30 meters. And so we can fill this in. P is equal to 1.01 times 10 to the fifth plus the density of seawater is 1.03 times 10 to the third times 9.8 times 30. And so you get that at 30 meters of depth, we have a pressure of 4.04 times 10 to the fifth pascals. Or in other words, if you divide that by atmospheric pressure, what you get is that the pressure at 30 meters below the surface is 4 times atmospheric pressure. And that's a lot of pressure when all of the closed compartments inside your body are at a pressure of 1 atmosphere. And in fact, when people dive down to depths like this, they have to regularly, as they're going, repressurize their sinuses and their lungs, and in order to be able to withstand this pressure. So now, what's the difference when we get to 150 meters? Well, again, the pressure at 150 meters is equal to the atmospheric pressure plus the density of the seawater times 9.8, but this time the change in heights is 150 meters, and so you get that the pressure is equal to 1.62 times 10 to the 6 pascals. And if you divide that by atmospheric pressure, you see that this pressure difference is 16 times. You're dealing with an external pressure on your body 16 times atmospheric pressure. Now we need to make one distinction here. This is what I'm going to call the true pressure. This is the actual force per area that the seawater is applying to the outside of the body. Often it's helpful to think of pressure in terms of how much that differs from atmospheric pressure. That is the pressure that can be read on most pressure devices. And that's called gauge pressure. So pressures are often given as what's known as gauge pressure. And in order to give the gauge pressure, you just need to subtract the atmospheric pressure from the true pressure. So the gauge pressure is equal to the true pressure minus the atmospheric pressure. Okay, well, let's think again about this pressure at 30 meters and 150 meters. So the gauge pressure at 30 meters depth is 16 times the pressure of the atmosphere minus 1 times the atmospheric pressure, which of course just gives you 15 times the atmospheric pressure. I did the one backwards. This is the one at 150 meters. And the gauge pressure at 30 meters of depth is 4 times the atmospheric pressure minus 1 times the atmospheric pressure, which gives you 3. And now you can see sort of a convenient little relationship between the depth below the surface of the sea and the gauge pressure. And that is for every 10 meters of depth, you gain about 1 additional atmosphere of pressure. Well, with this way of thinking, you can start to get a sense of the pressures that submersible vehicles experience as they descend. So, for example, let's think about the depth of the Titanic. And, you know, a couple of years ago, the Titan submersible, it was a big news story that this thing imploded as tourists were going to visit the Titanic wreck. Well, what's the gauge pressure that they were dealing with? They had 1 atmosphere of pressure inside the submersible. We're going to calculate the gauge pressure on the outside, which tells us what that pressure difference is that this submersible had to be able to withstand, and in the end wasn't able to withstand. Okay, so the Titanic wreck is at a depth of 3,800 meters. How many times atmospheric pressure did does a submersible experience? Geez, submersible. Well, as sort of a rule of thumb, this rule that every 10 meters corresponds to about 1 additional atmosphere of pressure, we would expect that this submersible had to withstand a gauge pressure of 380 times 380 times atmospheric pressure. Well, let's do the calculation to make sure that that's true. But yeah, we expect it to be about 380 times atmospheric pressure. To do the calculation, the pressure at the depth of 3,800, the lower point, is equal to the pressure at the top of the water. That's 1 atmosphere of pressure, plus the density of seawater, times the acceleration of gravity, times the depth of 3,800. This is the true pressure. And so this true pressure at that depth is equal to 3.85 times 10 to the 7th pascals. The gauge pressure is that true pressure minus 1 atmosphere of pressure. And so the gauge pressure on the outside of the Titanic is 3.84 times 10 to the 7th pascals. And now if you just divide that by 1 atmosphere of pressure, you get that, as expected, we have 380 times atmospheric pressure pushing on the outside. In the end, this submersible was not able to withstand that pressure. This idea, the relationship between the depth of a point and the pressure experienced by something at that depth, is used in common measurement approaches to pressure. So this relationship between the depth or height h and the pressure are used for measuring pressures. And I'm going to talk about 2 ways of measuring pressures. The first one is called a barometer. And this is used for measuring atmospheric pressure. I gave you what the standard atmospheric pressure is, but day to day, hour to hour, the atmospheric pressure is always fluctuating a little bit, and so this is a way to measure that. And the second measurement technique I'm going to give you is called a manometer. And this one is used to measure the pressure in an enclosed gas. Okay, so first I'm going to talk about the barometer. And the setup of a barometer is like this. You have a container holding liquid that's open to the atmosphere, and then you have a tube with the liquid inside it. So this is a liquid, and the liquid is able to climb up this tube. You want to use a liquid that at this temperature and pressure is going to have a low vapor pressure, which means this liquid is not close to boiling, and that means that the pressure up here in the empty part of this tube, this enclosed tube, is close to zero. We're going to assume that it's zero. Atmospheric pressure is pushing down on the fluid here that's open to the environment. So this is the atmospheric pressure. And by measuring the height between where the atmosphere pushes on the fluid and how high the fluid gets up this tube, we'll call this H, we can measure that atmospheric pressure. And so the formula for this, it really is the same formula we've seen before, but it says that you can measure that atmospheric pressure as the pressure at the top of the column of liquid. Well, we're assuming that pressure is zero, plus the density of the liquid times 9.8 meters per second squared times that height h. Okay, so the density here is not the density of the air, it's the density of the fluid, or the liquid in this case. Remember, fluid can be liquid or gas. We're talking about a liquid here. Otherwise, if this was a gas, this shaded area, it would flow out and equilibrate into the atmosphere, so it has to be a liquid. Okay, so this is a liquid. So let's see how this works in a calculation. What's the barometric pressure I'll call it P atmosphere. If the liquid that's used is mercury, and mercury has a density of 13,950 kilograms per cubic meter. And the resulting height of the column sorry, little technical problem there. If the height of the column is 0.72 meters. Okay, so if there was a barometer in your office that used mercury, probably wouldn't want it to be in your office, I suppose, if it's mercury open to the environment, but you know what I'm talking about. So you go to read this pressure in the atmosphere, you measure that column of mercury. It's 0.72 meters at its highest point, higher than the pool that's open to the atmosphere. Then the atmospheric pressure is equal to zero, which is the negligible vapor pressure of mercury at our temperature, usual temperatures and pressures, plus the density of mercury, 13,950, times 9.8, times 0.72, and that gives an atmospheric pressure of 0.984 times 10 to the 5th pascals. So if this column is 0.72 meters high, it means that the atmospheric pressure is slightly lower than standard atmospheric pressure. The second type of measurement technique, and the one that's more important for medical applications, is the manometer. And the manometer, rather than using to calculate atmospheric pressure, is used to measure pressure of an enclosed gas. So it looks something like this. You have an open tube. This end is attached to the enclosed gas. So the pressure on this end is the pressure of the enclosed gas that we're trying to measure. Inside the tube, again, we have a liquid that often would be mercury, sometimes water. This time, instead of the tube being enclosed at the top, being sealed at the top, it's open to the environment, which means the pressure at the top is the atmospheric pressure. The H for our calculation is the difference in heights. And so if we're trying to calculate the pressure of this enclosed gas, that pressure is going to be the atmospheric pressure plus rho times G times H. And again, this rho is the density of the fluid, of the liquid, which again, it could be mercury or water. And so this would be if you're calculating the true pressure. If you want to calculate the gauge pressure, then you'd subtract 1 atmosphere from your answer, which basically just cancels this first term, and you get rho G H. Medical calculations of pressure are going to be gauge, and so we're going to use this second formula. So this is the one that's going to be important for us. Well, let's do an example calculation. So let's say the enclosed liquid is mercury again. We already have talked about the density of mercury. And let's say that the gas pressure we're measuring we want to gauge pressure, and let's say that we know from some other way of measuring it that that gauge pressure is 0.5 times 10 to the 5th pascals. What would be the height of the column of mercury? Well, we're using this same formula that I just gave you, this boxed formula, but this time just instead of calculating the gauge pressure of the gas, we're given that and we're trying to calculate H. So we get that 0.5 times 10 to the fifth is equal to the density of mercury times 9.8 times H. Divide both sides by the stuff we're multiplying by H, and we get that the mercury would have a height of 0.366 meters. Well, as these two last examples show, there's always a relationship between the height of a column of liquid, mercury is the most common one, and a pressure. And so as the last two examples show, a pressure can always be represented, can always be described, pressure can always be described as the height of a column of mercury. Well, it doesn't have to be mercury, it could be other liquids too, but mercury is the most common one. And so traditional measures of pressure in medicine are given in terms of millimeters of mercury. So these are given in millimeters of mercury. And so when you see that unit of pressure, you can think of it as just the unit of pressure. It's given as mmHg. So that means that that pressure, the gauge pressure, I'll write that too. This is always a gauge pressure. Is being given as the height of a mercury column in millimeters. Okay, so let's see this in an example. So let's say we have a pressure of 2.4 times 10 to the fifth pascals, and we want to express that in millimeters of mercury. We're going to assume that this is a gauge pressure. And so we'll set it up as 2.4 times 10 to the fifth is equal to the density of mercury, 13,950 kilograms per meter cubed, times 9.8 times H. And again, we're going to solve for H. And we get that that difference in heights is 1.756 meters. Now we just have to put it in millimeters. And so this is 1,756 millimeters. So you could say that the pressure of this gas is 1,756 millimeters of mercury. Now, in a medical setting, one way this would come up is in blood pressure. So example, during a person's heartbeat, their blood pressure is going to be highest when the heart is contracting, is sending blood throughout the body, and it's going to be lowest away from that time of propelling the blood through the system. That higher pressure is the systolic pressure. The lower pressure is the diastolic pressure. So let's say that a person's systolic, the higher one of those two, blood pressure is 120 millimeters of mercury. First, let's calculate the gauge pressure in pascals. And then second, let's calculate the true blood pressure in pascals. That is just the total pressure that the blood is exerting on the walls of the blood vessel at the same height as the person's heart. Okay, well, for the gauge pressure, we're just going to take the density of mercury times 9.8 times 120 millimeters is 0.12 meters. So I want these all to be in the same units, all in SI units. And we get a gauge pressure of 16,405.2 pascals. Now, that's a gauge pressure, so in order to represent that as a true pressure, we just have to add 1 atmospheric pressure to this. So the true pressure is the gauge plus the atmospheric pressure. I'm going to use standard atmospheric pressure. And so we get 117,405 pascals, or you could write it as 1.17 times 10 to the 5th pascals. So maybe surprisingly close to atmospheric pressure for the highest blood pressure that you see during a heartbeat cycle. The last topic that I want to discuss in hydrostatics is buoyancy. Buoyancy. And the fundamental idea of buoyancy is when any object is submerged in a fluid, and usually we would do this with liquids, but it's true of gases too. But when any object is submerged in a fluid at rest, the fluid applies an upward force on the object and so that force partially or sometimes fully resists the acceleration of gravity, the force of gravity pulling it down. This is called the buoyancy force. And one thing that you need to keep in mind about the buoyancy force is if you have two objects that are the same size, that have the same volume, One is very dense, so very heavy. One is not very dense, so very light. The light thing is going to float, and the very dense thing is going to sink. But the buoyancy forces of those on those two objects are the same. The only thing that makes one float and one sink is that gravity for the very dense one is big enough to make that accelerate downward through the liquid. For the one that's not very dense, gravity, the weight force is not very strong, and so it's not enough to overcome the buoyancy force, and the object floats. So the buoyancy force, you need to remind yourself as you go through this that the buoyancy force alone isn't what tells you whether something sinks or floats. It's the combination of the buoyancy force and the weight of the object that determines that. The buoyancy force, and I'll call it F sub B, is always equal to the weight of the displaced fluid. If you want to make sense out of that, you can think about the fact that if the object wasn't there and that fluid were in place of the object, that fluid wouldn't move up or down. It would be held in place by that fluid. And so that buoyancy force must be exactly enough to balance out the force of gravity for that displaced fluid. This is called Archimedes' principle. And it says that the buoyancy force is equal to the density of the fluid times the acceleration of gravity in free fall times the volume of the object. Okay, so notice that in calculating the buoyancy force, the density of the object doesn't come into it. It's just how much fluid is displaced by the object. So that's the volume of the object times the density times gravity. All of this just gives you the weight of the fluid that is displaced. Okay, so now let's use this to calculate for an object that we know floats. When it floats, how much of the volume of this object is submerged in the water and how much is out of the water? So let's say that we have a block of wood with a volume of V. I'm just going to leave it as a constant like that. And a density of 400 kilograms per cubic meter. If we set this gently in still pure water, what fraction of the volume is submerged? You might have noticed before that if you compare two things that float, one that's more dense and one that's less dense, the less dense thing, say the lighter wood like balsa wood or something, will sit higher in the water. The thing that's more dense, even though it still floats, will have more of its volume underwater. So that's what we're going to calculate. For this density of wood, what fraction of its volume needs to be under the water for it to float? Well, I'm going to start with a free body diagram. And this is the block of wood, and it has volume V. And there are two forces acting on it. There's the weight force, and that is the density of the wood times its volume, which gives you the mass. So this is a mass of 400 times the volume times G. And now we have the buoyancy force, the thing that's new for this topic, and that is the density of water. The density of pure water is 1,000 kilograms per meter cubed, so this is 1,000 times the volume of the block that's submerged. Okay, that's the volume of the block that's underwater. So I'll call that V sub S times G again. And if this thing is floating, we're assuming that there's no acceleration. And so I'll put this into Newton's second law. I'll call positive up. And so we have 1,000 Vs times G minus 400 V times G. Those two volumes are different. This is the V is the full volume of the block. The Vs is the submerged volume. Divide both sides, this is equal to 0. Divide both sides by G. You can get rid of that. Add 400 V to both sides, and you get 1,000 V submerged is equal to 400 V. Now divide both sides by 1,000, and you get that the volume that's submerged is 0.4. So in other words, 40% of the volume needs to be submerged for this to float. Now there are two ways that this percentage could go down. The density of the block could be less, or the density of the liquid could be higher. So, for example, remember that I said the density of seawater is higher than the density of pure water. Not much higher, but a little bit, enough to make a noticeable difference in some things. And so what we would have then, if you go back to this equation, is 1,030 Vs is equal to 400, 400 V. And when you did that division, you would see that the submerged volume of this same block, but sitting in seawater, is 38.8%, just slightly less of that block needs to be submerged. An interesting consequence of that is speedboats actually go faster in seawater than they do in freshwater. At first guess, you might think that the salt causes more friction or something, but the main effect is that a boat that's driving in seawater is sitting slightly higher out of the water than a boat that's in freshwater. And sitting slightly higher reduces the friction on the boat. And so a boat that goes 80 miles an hour in freshwater might be able to go 85 miles per hour in seawater.